Okay, we are going to look at a problem where we have a sign attached to a beam, which is attached to a wall by a pin, and we have a cable that's also supporting the beam. And that sign has a mass, so this is a building, the sign has a mass of 73 kilograms. The angle that the cable makes is 23 degrees. The beam holding the sign is 8.4 meters long, and the cable is attached 3.4 meters from the wall. And the beam has a weight of 425 newtons. All right, so we want to answer two questions about this problem. The first is, what is the tension in the cable? So what is the tension? And the second is, what is the force exerted by the pin? Okay, the force, the magnitude and direction. All right, so the tension and the force by the pin are both acting on the beam. So our object is going to be the beam. And if these forces didn't exist, the beam would be in a state of rotation. So right now it's in a state of static equilibrium. So when we analyze static equilibrium, we're going to do a torque analysis and a force analysis. Either one of those relates to static equilibrium. So we start with one of them. Let's start with the torque analysis of the object on the beam, of the object of the beam. So we're going to draw an extended free body diagram of the beam. Thinking about the interactions, I'm not going to write them in the interest of space, but we'll talk through them. So what are the forces acting on the beam? Well, we know that there's a force of gravity. This is a uniformly distributed beam. I didn't mention that. It's uniformly distributed. I'll write that in here for our purposes of record. So uniformly distributed. Therefore, the force of gravity acts at the geometric center. So here's our force of gravity, which we know to be mg, which we also know to be the weight. So those go by, that's the same force. We also have the sign hanging off the end. So here's the sign hanging off the end. So this is the force of the sign, which is going to be the same as the force of gravity of the sign. Okay, so the force of the sign is exerting its weight at the end of that beam. And then we have the tension in the cable. So it's acting up and to the left there. So there is our tension. We know that angle is 23 degrees. And finally, the wall. So if that pin, if the pin wasn't there, the beam would fall down. So we know that the force of the pin vertical is up. And given the rest of the forces, it would move in that direction. So the force of the pin horizontal is to the right. Okay, so we want to determine both the tension and these two forces. We have to have both of them if we're going to get the force of the pin in total, the resultant force. Well, how do we strategize what we go after, where we set our pivot point? I don't know either of these two forces, and I don't know this one either. So that leaves me with three unknowns. But if I select my pivot point at this location, these go away from the torque analysis. There's no radii. And therefore, I might be able to solve for what I want. So we're going to set this at our pivot point. All right, when we do that, we need to identify both the radii and the angles for each force. So here is the radius for the force of gravity from the pivot point to the force. If I extend that radius and curl, this is the angle for the force of gravity. Similarly, here is my radius for the sign. If I extend, curl toward the force, this is my angle for the sign. And finally, here is my radius for the tension. And if I extend that radius, curl to the force, there is the angle for the tension. Okay, so our radius for the tension, we said that it was connected 3.4 meters from the pin. My angle for the tension, well, this angle was 23 degrees. 180 minus 23 is 157 degrees. It's in the counterclockwise direction, so it's positive. For my force of gravity, the radius of the force of gravity, it's in the geometric center. It's an 8.4 meter long beam. So the geometric center is 4.2 meters. Well, that was a terrible picture. I have to move that because that's awful. So I was doing it too quickly. Terrible, terrible, terrible. Let's move. If the geometric center is 4.2, then my 3.4 cannot be past it. There we go. Much better. All right, so we have 4.2 meters. My angle for the force of gravity is equal to, well, I extend that, negative, because it's in the clockwise direction, 90 degrees. Finally, I have the force of the sine. The radius of the sine is equal to that full length, so 8.4 meters. The angle that the sine makes, again, 90 degrees and in the clockwise direction, so negative 90. I'm not going to worry about my radii or angles for these two forces because they're at the pivot point, so I know their torques are going to go to 0. I will write them in my torque analysis to be explicit, but we're going to keep that in mind. So let's number all our forces, including those, just to be very clear. And we're going to look at the net torque, or the sum of the torques, and we know we're in static equilibrium, so those are going to equal 0. So we want to consider the torque from force 1, 2, 3, 4, and 5. So every force could exert a torque depending on where we put that pivot point. For force 1, just to keep in mind our relationship, torque is the force times the radius times the sine of the angle if you use the method that we've been modeling, okay? You might need to reconsider that if you're only looking for the perpendicular component, because it is only the perpendicular component of the force that causes the torque. So if you use a different angle, make sure you're identifying the correct perpendicular component, which is what this gives if you use the angle I've shown you. So we have the force of the pin vertically times the radius of the pin vertically times the sine of the angle of the pin vertically, but we know that radius is equal to 0. We have the force of the pin horizontally times the radius of the pin horizontally times the sine of the pin horizontally, but that torque is also equal to 0 because the radius is equal to 0. We then have force number 3. So that's our force of gravity. So we have the force of gravity of the beam times the radius of the force of gravity times the sine of the angle for the force of gravity. So the force of gravity of the beam is its weight, so we have 425. The radius is 4.2 times the sine of the angle, which is negative 90. For the fourth force, the sine, excuse me, we have the force of the sine times the radius of the sine times the sine of the angle of the sine. The force of gravity of the sine is equal to the force of the sine, so that's the mass of the sine times g, times the radius of 8.4 times the sine of the angle, where that angle is negative 90. All right, then we have our final force, the tension. So that's the force of the tension, tension T, times the radius of the tension times the sine of the angle for the tension. So we have our tension, which we don't know, we'll call that T. It acts at 3.4 meters radius, and the sine of positive 157. So again, the sum of these torques are going to equal 0. So we have 0 plus 0. The torque for gravity is 425 times 4.2 times the sine of negative 90, which is negative 1. So we get negative 1785. Now, does negative make sense? Negative tells me that if that was the only force acting, it would rotate the object in the clockwise direction. And indeed, the force of gravity is trying to do that. Our force of the sine is the mass of the sine, so 73 times 9.8 times 8.4 times the sine of negative 90, which is negative 1, minus 6,009 Newton meters. And again, it's negative. It would rotate it in the clockwise direction. Plus the tension, which we don't know, times 3.4 times the sine of 157, which is 1.3. Well, the sine of 157 times 3.4 is 1.3. So we just get t times 1.3, and that, again, is equal to 0. So solving for t, add both of these to the other side. 1785 plus 6009. And divide by 1.3. And our tension is equal to 5,995 newtons. So using our torque analysis, we can get the tension in the string. All right, but we also want to know the force of the pin. Well, I'm not going to know that angle given the information I'm provided in the problem. So we're going to look at our force analysis to determine the force of the pin. I'm going to erase my tension analysis, or excuse me, my torque analysis really quick. Ugh. And we are going to look at a force analysis to determine the force that the pin exerts on that beam. So, if we're going to do a force analysis, we have to draw a free body diagram. And the same forces on a free body diagram are going to show up on the extended free body diagram. We're just taking this extended free body diagram and we're collapsing it to a single point. So we'll do a free body diagram on the beam. So everything collapses to a single point. But all 5 forces show up. So we have the force of gravity. The forces haven't changed. We have the force of the sine. We have the horizontal force of the pin. We have the vertical force of the pin. And we have the tension. So I literally just took this extended free body diagram and I collapsed it to the center of mass. So those are our forces. They're the same 5 forces, and we're going to number them the same to be consistent between our 2 analyses. So, what do I do with a force diagram? I break them up into their horizontal and vertical forces. I have 5 of them. Force number 1 is my vertical pin force. It's in the positive direction. It's the force of the pin vertically. Force number 2 is my horizontal pin force. It's in the positive direction, only in the horizontal. Force number 3 is my force of gravity. It's in the vertical direction, minus the weight. Force number 4 is the force of the sine. It too is in the vertical direction, and it's pointing down as well. And force number 3 is my tension. There's a component in the horizontal direction and a component in the vertical direction. The component horizontally is negative. The component vertically is positive. We know this angle is 23 degrees. So our horizontal component is minus the tension times the cosine of 23. Our vertical is the tension times the sine of 23. All right, just like with any forces, in any force analysis, if we took the sum of the forces horizontally, it's going to equal the mass times the acceleration horizontally. And if we take the sum of the forces vertically, it's the mass times the acceleration vertically. Well, this object's in static equilibrium. So those are both 0. All right, so let's sum them up. We have the force of the pin horizontally minus the tension times the cosine of 23. That's going to equal 0. And we have the force of the pin vertically minus the weight minus the force of the sine plus the tension times the sine of 23. And that's going to equal 0. Now we can simply solve for the force of the pin horizontal, which is equal to the tension times the cosine of 23. Our tension, which was 5,000, remember T, I'll just write it over here for remembering, 5,995. So 5,995 times the cosine of 23 gives us the force of the pin in the horizontal direction is equal to 5,519 newtons. And the force of the pin vertically is equal to the weight plus the force of the sine minus the tension times the sine of 23. So our weight was 425 plus our force of the sine, which was the mass of the sine, 73, times 9.8, minus the tension, which was 5,995 times the sine of 23. And we get the force of the pin vertically is equal to, I think I might have done something incorrectly. So the force of the pin, let me just redo it. 425 plus 73 times 9.8 minus the 5,995 times the sine of 23. I'm running out of room. 5,995 times the sine of 23 is 2. Oh, this is exciting. Is 2. Let me move it over here. I'm moving it too little space. So we're on the force of the pin vertically is equal to 425 plus 73 times 9.8, 715.4 minus 5,995 times the sine of 23, 2,342, and I'm smiling because I like what this is going to do for us from a teaching standpoint. So if I add those all up, I get 425 plus 715.4 minus 2,342, and I get negative 1,201, which means I get a negative vertical force. Is that possible? Well, yeah, I was making a guess as to what direction the vertical force was. It's possible that the wall is preventing it from being pulled upward, perhaps by that tension, than from falling. So, it tells us that the force in the vertical direction is negative. Now, what do I do with those two? Well, we know that the force of the pin magnitude is equal to the square root of the force of the pin horizontally squared plus the force of the pin vertically squared. So, the square root of 5519 squared plus negative 1201 squared gives us 5,648 newtons. But we also need the angle, which is the inverse tangent of the vertical component, negative 1201. I am really running out of room. Over the horizontal component of 5519. So the inverse tangent of negative 1201 divided by 5519 gives me negative 12 6.3 degrees. And it is in the correct quadrant. All right, so we found the tension through a torque analysis. We found the forces through a force analysis of the pin. We have to remember to put them together and get that angle. We have to remember to check the angle direction because of the way the tangent works mathematically versus physically. We see a negative vertical, positive horizontal. We are in the correct quadrant. Whew. All right, good job.